We have learned about how shape symmetry and charge symmetry, which is determined by bond dipoles and lone pairs and that sort of thing, can make a molecule polar or non-polar. With extended octet, we need to think of new shapes in a three-dimensional way, and that's a little bit tricky. So I've gone through two sulfur fluorine molecules as examples for how to look at their polarity. So SF4, I haven't done the full Lewis structure because I haven't got the lone pairs around the fluorines, so therefore this is just a three-dimensional diagram here, is an example of a polar molecule. So sulfur tetrafluoride is polar. And the reason is that we've got this lone pair, so therefore we've got asymmetry of shape. So automatically we know that it's going to be polar. But which side is delta minus and which side is delta positive? Well, for that, we need to look at the bond polarity. Fluorine has got a much higher electronegativity than sulfur, so all of these are going to be bond dipoles. In three dimensions, these two dipoles, these two SF bonds, are actually going to cancel out. One's going left, one's going right, and they're the same size, so they cancel out to zero. These two at the bottom, though, do not cancel out. They're balanced out by a lone pair of electrons up here. So this is just a lone pair of electrons. Lone pairs do not create a dipole moment because they're not bound to anything. So we're looking here at these two dipoles are creating a pull in the downward direction. So the sum of those two dipoles would be down. So this side of the molecule would be delta negative, would be slightly negative, and this side, or this pole of the molecule, would be slightly positive, even though it's got a lone pair of electrons there. And that's because of those dipole moments. Now, conversely, SF6, which has got exactly the same bonds in it, is non-polar. And the reason for that is that in three-dimensional space, the corners of an octahedron, all of those dipoles are pulling in opposite directions to each other, across 180 degrees from each other. So they're cancelling each other out, creating a non-polar molecule because it has symmetry of shape and symmetry of charge distribution due to its dipoles. So these two molecules show quite a nice example of how to apply the extended octet rule to assigning polarity to a molecule. The next one I'm going to look at is xenon tetrafluoride, because that's an interesting one with lone pairs of electrons, but it's a non-polar compound. So I'm going to get rid of my SF6 for this one and show you xenon tetrafluoride. Now, xenon is a noble gas, so you wouldn't expect it to bind, but it does. So if I drew this one, I've got a lone pair above, a lone pair below, a fluorine there, and on the same line, so 180 degrees away, I've got another fluorine. I've got a fluorine out here, 90 degrees away from that one, and again, 180 from there, I've got a fluorine. Now, xenon's electronegativity is very low, so you've got these two dipoles cancelling each other out. You've got these two dipoles cancelling each other out. This lone pair is 180 degrees away from this lone pair. One up, one down. They cancel each other out. Any effective of charge distribution that a lone pair could create is also cancelled out. So you've got a symmetrical shape where the bond dipoles have cancelled out. You've also got some lone pairs, but because there's symmetry, there's a lone pair above the xenon and one below, this ends up being a non-polar molecule. And that's probably about as hard as they get, this xenon tetrafluoride example.